Hi there. Today we are going to be completing Chapter 10, which should finish off Math 356. We're going to be doing some advanced stuff today. And so when we think about what Math 356, BioCalculus Part 2 has been about, we've done a lot of different topics. We started by reviewing all of BioCalculus Part 1. Then we focused on differential equations a little bit more with Chapter 7. Then we went into matrices with Chapter 8. And then we did multivariable calculus in Chapter 9. And now we're going to be taking those last three big topics and kind of merging them together for Chapter 10. This is the chapter where we take all of our thinking from throughout the semester and kind of unify it. We are going to be dealing with systems of differential equations and chaos theory. The idea behind systems of differential equations is instead of a single differential equation, we are going to be dealing with two at the same time. In the real world, when you're modeling, you're going to be dealing with more than two, but we're just going to be starting with two so that we can understand the fundamentals. We're going to be using vectors and matrices in order to do this, because that's the easiest way to model things in 3 dimensions. We're going to be needing the eigenvalues and eigenvectors of our systems in order to determine stability, whether things are stable, unstable, as well as thinking the multivariable calculus, we're going to be having some nodes which are saddle nodes. And so visualizing things in 3 dimensions could be beneficial here. We're going to be dealing with 3 variables, time, and then 2 spatial dimensions. And so that's also a Chapter 9 idea. But at the heart, it's all differential equations and how we can solve them. When we think of 7.5 and 7.6, those 2 sections are going to be essential in understanding the Chapter 10 material. And so make sure that you feel very comfortable with those 2. That said, we're also going to be talking about the idea of chaos theory, the idea that a small change in initial conditions can have a substantial difference on the system of differential equations. A small change can have a massive change on the outcome of whatever you're dealing with. If you think about the heart, well, if you are a centimeter off in the heart, that's a big difference. And so we're definitely going to be dealing with things like that. We're also going to be exploring how we can solve nonlinear systems of differential equations, which are a little bit trickier. And we're also going to be trying to understand some models. And so we have a lot of different things we're going to be doing today. We'll see how we do. We're going to start with just some definitions, though. And we're going to try and get our systems of differential equations idea down to something which is a little bit manageable for us. And so a 2-dimensional system of linear differential equations, and so now it's a linear differential equations, is a system of differential equations which can be written in the following form. dx dt equals a of tx plus b of ty plus g1 of t. dy dt equals c of tx plus d of ty plus g2 of t, where a, b, c, d, g1, and g2 are all functions of t. Now, that's a lot of functions of t already, and so we could be dealing with a mess. What's interesting, though, is that we can write this in matrix form. We usually use the dot notation when we're talking about derivatives in matrix form. And so if you see an x dot, note that that is just saying dx dt, or the rate of change of x. Same with y dot. Y dot corresponds to the derivative. Instead of using the apostrophe or prime symbol, we can use the dot. This is Newton's notation for it. But we can rewrite this system of equations as this one equation with matrices and vectors. Often you'll see this written in the following format. X dot equals a of tx plus g of t, where again, xy is our x vector. X dot y dot would be x dot, the derivative of this vector. And then we have a vector for shifting things, and then we have a matrix. The benefit of this notation is that it's easy to expand this into higher dimensionals. And so here's an example where we have a 5-dimensional system. And so now it's x1 dot, x2 dot, x3 dot, x4 dot, x5 dot. Well, that could still just correspond to x dot, where the vector x is x1, x2, x3, x4, x5. Our A of t then is a 5 by 5 matrix, and we can have a 5 by 1 vector over here to correspond to how things are shifted. Thinking about higher dimensions, each dimension doesn't necessarily have to correspond to a spatial dimension. This is very important when we're dealing with this stuff. We're not thinking about graphing in 5-dimensional space. That's not a thing we're going to be doing. Instead, we can think about these in terms of populations. And it doesn't have to be populations like an ecology population, such as wolves and rabbits and field mice and beavers and whatever other animals you want to throw into the mix. Instead, we could be talking about quantities of a chemical in a certain location. We could be talking about cells. We could be talking about blood cells, white blood cells, red blood cells, viruses. There are a lot of different things that these can represent. It's not just space. Each of these can represent some different quantity that you want to keep track of. And often when we're developing and exploring models, that's what we're going to be seeing. Now, the next key term to try and make it even simpler is autonomous. And so a system of linear differential equations is said to be autonomous if it is independent of time. In this case, a 2-dimensional autonomous system can be written as this. X dot, y dot, and again, this is an autonomous linear system, but it's x dot, y dot equals ABCD, XY plus EF, where all of those variables, A, B, C, D, E, F, they are now just numbers. And so that's much nicer. We've gotten rid of time. And in theory, if we're dealing with a system which is contains all factors, time won't be an issue anymore. If you think about it, the universe doesn't really carry a pocket watch. And so it does not care if it is 3 in the afternoon or 7:30. And so if we are taking everything into consideration, time won't be a component. Getting systems like that, though, is very difficult. Often you'll also see this written in this format, which is just the same format that we saw before. We're typically more interested in the cases where there is no B vector, though. As solving this case, x dot equals ax is usually sufficient for analyzing the structure of a differential equation or differential system. The reason for that is the B term is really just shifting things away from the origin. That's all it's going to be doing. And so if we just get rid of that B term, it'll just shift things back to the origin. And so a system of linear differential equations is said to be homogeneous if it can be written as either x dot equals ax or x dot equals a of tx. The ax here is saying that we're just dealing with an autonomous system. A of t would be non-autonomous, where there's some functions of t in here. We will primarily be focusing on the case where our differential system is both autonomous and homogeneous, and can therefore be written in the following 2-dimensional case. X dot y dot equals a, b, c, d, x, y, where a, b, c, and d are all real numbers, and x of t and y of t are some parameterization. And we can think of it as parameterization, much like we did in section 7.5. So this would be x of t, and this is x prime of t. We'll have y of t and y prime of t. And we could break this back into equation form. And so this would be x prime of t is equal to ax plus by, and y prime of t is equal to cx plus dy. And so we can go back and forth between those two if we want to. But now that we see the format that we have here, the only zeros, or typically the only zeros of this system, are going to be when both x and y are 0. Using that, we can start to find some equilibrium. So given a system of differential equations, an equilibrium of the system is a point where the system remains fixed. In the 2-dimensional case is where both dx dt and dy dt are 0. When we're dealing with a nonlinear system, we can use the nullclines in order to find those equilibrium, which is what we did in section 7.6. In the two-dimensional case, which we were just discussing, the two-dimensional, linear, autonomous, and homogeneous case, the only case where this is going to happen is at the point 0, 0. And so that means the vector 0, 0 will always be an equilibrium value, and it's typically going to be the only solution. Not always. There are some weird cases out there. For instance, if you have a matrix which is all zeros, then every point is going to be a fixed point. But that's not a very interesting system. And so typically, 0, 0 is going to be the only solution. Given the autonomous and homogeneous system of differential equations, x dot equals ax, the vector 0, 0 will be the only equilibrium provided the determinant is not equal to 0. This is often called the generic case or the general case. If the determinant of a is equal to 0, then there will be an infinite number of equilibrium values. This is called the non-generic case. We are not going to be dealing with the non-generic case. We're going to be focusing on the generic case for this course. The reason for that really is just that there's so many additional cases, and our course is more of an introduction to the ideas. As it is, we're going to be finding that we will be classifying our systems of differential equations into 6 different classifications. And so we already have a large task ahead of us. Adding the non-generic cases would really double the number of classifications that we have, and we just don't want to have to deal with that. And note, we're still just talking about the same type of differential equations we dealt with in chapter 7. The only difference is that we are greatly simplifying the problem. Instead of having multiple equilibria and having to find them, we're going to limit it so that we only have to find one equilibrium, which will always be at 0, 0. This way, we can work to better understand how these equilibria work when they're in a nonlinear system. And of course, we will be revisiting nonlinear systems before the end of today. But now that we have our system, and our system is x dot y dot equals abcd xy, it turns out that we can find a general solution very, very quickly. And it's using the eigenvalues and eigenvectors. And so xy is going to be equal to a, which is just an arbitrary constant, much like our plus c used to be. So it's a c1 e to the lambda 1 t plus b c2 e to the lambda 2 t, where c1 and c2 are the eigenvectors of the matrix, and the coefficients are, and lambda 1 and lambda 2 are the corresponding eigenvalues. And so this is the general solution. Proving that is a little bit beyond our course, as many things are. Essentially, these eigenvectors form a basis for the solution, but basis is a linear algebra structure. You will learn a little bit more about this if you take a linear algebra class. You'll learn a little bit more about this if you take a differential equations course. For our purposes, this is what the solution is going to look like, and now we need to be able to evaluate it and understand a little bit more about what the different classifications are based on this solution. Note that this formula will only work if lambda 1 and lambda 2 are not the same value. If they are the same value, this is a case called repeated roots, and the strategy for finding the general solution is quite a bit harder. We're not going to be dealing with that, and so that's a good thing. We also typically only use this particular formula, provided the eigenvalues are real numbers. When we have complex eigenvalues, we have an alternative formula which we can use based on the identity e to the a plus bit equals e to the at cosine of bt plus I e to the at sine of bt. That's something that comes from a trigonometry course when you explore, what's it called? Complex numbers in a little depth. We will be discussing this case. And so complex eigenvectors or complex eigenvalues are fair game. But we're going to start with the real case because we want to make sure we got the real case down first. If we wish to, we can also break up the solution so that we have distinct formula for x of t and y of t. And we'll see what that looks like when we're doing it. And final note, If we are given some initial conditions, we can use the initial conditions to determine what the constants A and B are. And so we can actually find A and B if we actually have an initial condition. And so here is our general strategy for real valued eigenvalues. And so to solve a homogeneous linear system of differential equations, begin by finding the eigenvalues lambda 1 and lambda 2. And so you can write the system in matrix form if needed. You can find the characteristic equation, ideally just using the trace and the determinant. Then you can solve the characteristic equation. You then need to find the eigenvalues, C1 and C2. Solve the system A minus lambda I times Ci equals 0 for both eigenvalues. We're then going to write out our answer in the form xy equals A times C1 e to the lambda 1t plus B C2 e to the lambda 2t. Alternatively, we can break the system up and write out the solutions for x and a solution for y as separate equations. Usually we're just going to keep it in matrix form, though. I mean, it's a nicer way of writing it. And then if you are given an initial condition, use them to evaluate the constants A and B to find the particular solution. Personally, I like the general solution a little better, but that could just be me. Let's try one of these and actually do a little bit of math rather than just talking the entire time. And so let's do number 1 just as a beginning problem. It's dx dt is equal to 2x plus 3y. dy dt is equal to 4x plus 3y. Let's figure this one out. And so in order to solve this one, what we need to do is we need to find the eigenvalues and eigenvectors. To do that, we need to first get this so that it is written in matrix form. And so let's write this in matrix form real quick. We are going to get x dot, y dot equals 2, 3, 4, 3 times xy. And so now we need to figure out our eigenvalues for this system. And it might make sense to actually write out the system with the eigenvalues written in it. And so write the matrix out so that it is A minus lambda I is equal to 2 minus lambda, 3, 4, and 3 minus lambda. The reason I did that is because eventually we're going to need to find the eigenvectors, and having this will make it so that it's easier to find the eigenvectors down the road. And so once we have this, we can use our characteristic equation, which remember is lambda squared minus the trace of this. And so 2 plus 3 is 5 lambda plus the determinant. Well, 2 times 3 is 6, 4 times 3 is 12, 6 minus 12 is going to give us a minus 6. And so lambda squared minus 5 lambda minus 6 equals 0 is our characteristic equation. That factors very nicely. And so when we factor this, we are going to get a lambda minus 6 and a lambda plus 1. We can now set each of these equal to 0. And so we're going to get lambda 1 is equal to 6, and lambda 2 is equal to -1. Now that we have our eigenvalues, we can figure out what the eigenvectors are. And so we can plug these in here and try and figure out our eigenvectors. And so for lambda 1, which is equal to 6, our eigenvectors are going to come from plugging the 6 in here. So 2 minus 6 is -4. Then we have 3, 4, and 3 minus 6 is -3. This times xy needs to be equal to 0, 0. And so the eigenvector xy, which is going to give us 0, 0, we could do a 3, 4. Remember, there's an infinite number of solutions. We just need an example which is non-zero. And 3, 4 would be 3 times -4 plus 4 times 3 equals 0. And so that would work for our first eigenvector. For our second eigenvector, that's -1. So we can take the -1 and plug it in. 2 minus -1 is going to give us a 3, then a 3, a 4, and 3 minus -1 gives 4. Oh, put that in the wrong spot. Lambda 2 equals -1. We are going to get 3, 3, 4, 4 times xy equals 0, 0. In this case, I might go with 1, -1. Because 1 times this plus -1 times this equals 0. Well, we now have two eigenvalues and their corresponding eigenvectors. We can write out our solution. And so our solution is going to be xy is equal to a e to the lambda t, so e to the 6t, times our eigenvector, 3, 4, plus b e to the -1t times 1, -1. And that's our general solution. Now, if you wanted to, you could break this apart. I wouldn't recommend it, but you can if you want to. And you can see how this would be written as parametric equations. And so if we were to break this apart, we would say it's going to be the top row, which is x equals, I guess we could say x of t equals, it's going to be 3a e to the 6t plus 1b e to the -t, and y of t is going to be equal to 4a e to the 6t plus, well, now it's going to be a minus b e to the -t. So this is the set of parametric equations which are defining the solution. Now, note that we do have the a and b in here. The a and b are really going to be tied to whatever initial conditions you are given, if you are given initial conditions. It turns out there's an infinite number of curves that this could take, depending on what your starting value is, depending on what your a and b values are. In order to get a particular solution, you would need to be given some initial condition. And once you had an initial condition, you could solve for a and b and get your particular solution. I believe we'll see that with our next practice problem. And so for our next problem, number 2, it's the same process. But now we're given an initial condition. And so the problem we are given is x dot, y dot, and I'll just write it in matrix form initially. It's 3, -2, -2, 3 times xy. And we're also given an initial condition. In this case, it is x of 0, y of 0 is equal to 1, -1. That should allow us to find a particular solution. And so let's go through this process again. The nice thing is it's going to be very formulaic. Every single problem is going to be the same type of process. And so we will do a minus lambda I just so that we can see what our matrix with eigenvalues is going to look like. And in this case, it's going to be 3 minus lambda, -2, -2, 3 minus lambda. We then do our characteristic equation, which is lambda squared minus the trace, which is 6 lambda, plus the determinant, which would be 9 and 4. 9 minus 4 gives us 5. That factors very nicely, so we are going to get lambda 1 is equal to positive 5, and lambda 2 is equal to positive 1. And if you want, you can actually show the factoring step and make sure you don't make a sign mistake. Sign mistakes are the number one issue that folks have with these problems, and so be very careful. But once we have that, we can use our eigenvalue 1, which is 5, and we can create the corresponding matrix. And so the corresponding matrix for the first eigenvalue is going to be given by 3 minus 5, which is 2, -2, -2, and then 3 minus 5 is 2. Oh, wait, -2. I made a sign mistake. Like I said, sign mistakes are going to be the issue we're going to have the most. For the most part, they're easy to catch, but not always. And so -2, -2, -2, -2 times xy equals 0, 0. That tells us that our corresponding eigenvector is going to be 1, -1. Because 1 times this plus -1 times this equals 0. For lambda 2 equals 1, same process. 3 minus 1 is going to be 2. -2, -2, 2. Times xy equals 0, 0. So our corresponding eigenvector in this case is going to be 1, 1. And so now we have the eigenvectors and the eigenvalues. We can write out the general solution. And so our general solution in this case is going to be xy is equal to a e to the lambda t, so e to the 5t times 1, -1, plus b e to the lambda t, and so b to t, and then it's going to be c2, which is 1, 1. So this is the general solution, but we weren't looking for the general solution in this case. We were looking for the particular solution. We were given initial information, and so we can use that to find the particular solution. And so we need to take this point and plug it in. And so x of 0, that's going to be when t is equal to 0. Well, when t is equal to 0, e to the 5t is 0. E to the 5t is 1, and e to the t is also 1. And so we are going to get xy is equal to a times 1, -1 plus b times 1, 1. But we're also told that at this point, xy is equal to 1, -1. At this point, you might be able to just look at it and see the solution. If you don't, you can break this down. You could say that 1 is equal to a plus b. -1 is equal to -a plus b, just by distributing the a through to each and the b through to each. But our solution in this case is going to be a is equal to 1 and b is equal to 0. And hopefully you can see that pretty quick. Once we have that, we can plug that in and get our particular solution. So a is 1, b is 0. That means this term It's gone. And so our particular solution is xy is equal to 1 e to the 5t times 1 negative 1. Again, if you want to, you can write this in its parametric equation form. And this would be saying that x of t is equal to e to the 5t, and y of t is equal to negative e to the 5t. Usually I would just keep it in the matrix form, or the vector form in this case. It just makes it a little bit cleaner and easier to read, especially if you need to do additional things to it. The remaining two problems here are fairly similar. Number 4 is actually a lot more difficult because I made it x of 1 and y of 1. That definitely makes things a little bit trickier, but it's just a lot of algebra and a little bit more computationally difficult. Instead, we're going to be doing these problems again very shortly, but before we do, I want to show you what the graphs of these look like. And so we can use the eigenvalues and the eigenvectors to sketch the phase portraits. If you recall from chapter 7, we were able to graph phase portraits using the null lines. The null lines would be telling you where things are equal to 0, where they're flattening out, either in the x direction or the y direction. Well, that's a great way to do things, especially when you have a nonlinear system. But when we are dealing with a linear system like we are, we can actually use the eigenvectors to get a much more exact solution. And so consider the system of differential equations here, x plus y and 3x minus y, or we can write it this way. To the right, and so right here, is a graph showing the phase portrait for this system. Notice how the phase lines all seem to approach or run away from the same general lines. So in this case, they are approaching in this direction, and then they are running away in this direction. Turns out the solution for this equation is given by a negative 1, 3, e to the negative 2t, and b, 1, 1, e to the 2t. Those eigenvectors are going to be telling us what the lines are that we are approaching. And so looking at the example, we can actually draw those lines in. Here is the negative 1, 3 line coming in, and it's coming in both directions. And here is the second eigenvector, 1, 1. Notice how that's going out in both directions like that. Eigenvectors by design keep vectors going in the same direction. That's how we defined them at the beginning, which means that they are our equilibrium lines. Depending on the eigenvalue, it'll determine whether or not it is going in or out along that eigenvector. And so negative eigenvalues mean that the system is approaching 0 along the eigenvector, while positive eigenvectors mean the system is approaching infinity along the eigenvector. And so if it is a negative eigenvalue, it's coming in. If it's a positive, it is going out. That gives us 3 different cases that we could have for real eigenvalues. And so provided our eigenvalues are real, non-zero, and distinct, there are 3 main cases we will consider. An unstable node, in this case, both of the eigenvalues are positive. This is also sometimes called a source. A stable node, in this case, both eigenvalues are negative, and this one is sometimes called a sink. And then a saddle point. In this case, one eigenvalue is positive and the other eigenvalue is negative. We are going to be able to do these graphs by hand, just using the eigenvalues and eigenvectors. And so here are the 3 cases. The first is an unstable node. And so let's say 0 is less than eigenvalue 1 is less than eigenvalue 2. And here is a sample example. And so notice we have our 2 lines. And then if we look at this, we can see how everything is going away from the origin. Eigenvalue 2 is 3, eigenvalue 1 is 1, and everything is going away from the origin because along both eigenvectors, it's going away. But notice that it's going faster in one direction than it is the other. And that's causing it to kind of curve out in one direction. And it's curving out in one direction where the eigenvalue is greater. That's because when we think of the general solution, this term, the second term, has that 3t there. That's a larger eigenvalue. And so that tells us that it is going faster in that direction, faster along that eigenvector. And so when we are graphing these, we're going to graph the two eigenvectors, and then we are going to make sure that we curve it so that it is going more in the direction of the eigenvalue, which is larger. The exact same thing happens with the stable node. So in the stable node case, both eigenvalues are negative, and so everything is coming towards the center. But notice we have the -3 term and the -1 term. Well, -3 is a larger negative value, meaning that it's a larger number in absolute value. And so that tells us that it is going faster towards 0 in that direction. And since it is going faster in that direction, things are going to be curving as though it is going towards this line here, but then it's starting to curve in. The third case is the saddle point. This one's the easier of the three because you have one which is going in and one which is going out. And the curves are just going to be going from the one going in towards the one going out. It can be a little tricky to graph, but it is very doable. Now, I do want to point out that we do have tools that we can use to graph this stuff. If you want, you could use Desmos. I actually made something last night in Desmos, which will graph this stuff for us if we want to. If you want, over here on the left side, you can see the equations that I used, at least some of them. There we go. And, you know, it took a little bit of work. I spent probably a half hour making it. But you can do this if you want. Oh, and here's that there. The trick was making the vectors. Once you are able to make the vectors, it's much easier. But with this, I made it so that we can type in any equation we want in here, and then it'll show where things are increasing. The orange regions are where things are going in a positive y direction, so you can figure out what direction the arrows would be going. I've got the null lines on here, and then I've also created a point which is movable so that you can figure out exactly where things go. If you want, you can make something like this. I would probably recommend instead you use a program like pplane. And let's see if I have pplane up. I do. And so here is pplane. Pplane is a JavaScript or Java app, which is used to graph these things. There are others out there, and I think pplane recently has been using MATLAB, and so you might need an older version of pplane to get it to work correctly for you. But the nice thing about this is it shows the phase lines, and so we can type something in here. Let's say that we wish to do 2x plus 3y, and then how about a 3x minus 5y? We can graph that, and it will graph things very nicely for us. And we can do all of the phase lines we like. It'll find the equilibrium for us. It'll even classify them for us if we ask it to. And so it's a very versatile program. There are others out there. If you look up a vector field analyzer, you might be able to find one. But because of the technology, they come and go periodically. That said, we're going to learn how to do this stuff by hand. And so let's figure out how we can do this by hand. Oh, and as mentioned earlier, there are a number of different cases that can happen based on the eigenvalues. In general, a system is stable if the real parts of both eigenvalues is less than or equal to 0, and unstable if either eigenvalue is greater than 0. And so that's going to be what we're looking for. And so here's the general strategy for drawing phase portraits for linear homogeneous systems. Find the eigenvalues and the eigenvectors. Draw the eigenvectors on the graph with arrows outward if lambda is positive, and with arrows inward if lambda is negative. And then fill in the remaining regions with the appropriate curves with arrows pointed in the directions they are going. So let's try some. And so let's try this first problem here. We are going to find the general solution. We're going to use the eigenvalues and eigenvectors to draw out the phase portrait, and then we are going to classify it as a stable node, an unstable node, or a saddle. Let's see if we can figure this one out. And so it is x dot, y dot equals 3, -4, 1, -2. All right. And so for this one, solving it is going to be the exact same process that we've already done. And so we can create our A minus lambda I matrix to make things easier for us later. It'll be 3 minus lambda, -4, 1, and -2 minus lambda. We can then use the characteristic equation, which is lambda squared minus the trace, which would be -1 lambda, plus the determinant, which is -6, plus 4 is a -2. Those easy computations are the easiest ones to get wrong, and so be careful. This factors to be lambda -2, lambda +1. And that tells us that lambda 1 is equal to a +2, and lambda 2 is equal to -1. Already, with this information, we can classify this system. This is going to be a saddle point. I'll write that up here. This is a saddle point. And we know that because we have a positive and a negative eigenvalue. And so now let's find the general solution, because we need the eigenvectors in order to graph it anyways. And so for lambda 1 equals 2, we are going to get 3 minus 2 is 1, -4, then -1 and -4. xy equals 0, 0. Well, that tells us that we are going to have a 4, 1 as our first eigenvector. For eigenvalue 2, which we're saying is equal to -1, we are going to have 3 minus -1 is 4, -4, 1, then -2 minus -1 gives a -1. And so for this one, we can draw a better C. And that's going to be a 1, 1. And so we have the general equation now. The general solution is going to be given by xy is equal to a e to the 2t 4, 1 plus b e to the -t 1, 1. The last thing we'd like to do is we would like to graph this. And so let's draw the phase diagram for this system. In order to do that, we need to have a Cartesian coordinate system. And so let's see if we can make a simple Cartesian coordinate system. Oh no, my pen is running out of ink. That's all right. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. All right. While we do that, I'm not even going to pause the video while I create new ink in here, because it's always fun to see how the ink gets put in. There we go. And just like that, we have new ink. And so we're going to do these two eigenvectors. And so the first eigenvector is 4, 1. Remember, this is x and y. So we're going to go 4 in the x direction and 1 up. And we're going to have a vector which is going through that point. We're going to do the same down here, because it's going to be going in both the positive and the negative direction. And try and clean it up a little bit. I'm not so good at drawing today. Our other one is going to be 1, 1. And so that'll be coming up like this. And so for our first one, C1, 4, 1, our eigenvalue was a positive 2. That tells us that it is going out in that direction. For C2, we saw the eigenvalue was negative 1. That means that it is going in that direction. Curves then are going to be going from the one going in towards the one going out. So it'll be coming in like this, then it'll start to curve. It'll never cross the eigenvectors because that's what it's approaching. But we will see down here, it'll come in, then it'll start to curve away. Over here, same thing. It's going to be coming in, and then it's going to curve towards it. Same over here. It'll come in, and it'll start to curve. And so this is what the graph should look like. The phase portrait, phase diagram for this. If we want, we can check. And so let's see if we can check using our program p-plane. Well, actually, let's use this one that I created just the other day, or yesterday, actually. It was 3x minus 4y, and it was x minus 2y. And we can see already that the curves are doing what we said they were going to do. And so on the top, it is coming almost straight in this direction, but it does start to curve a bit. Down here, it's going in the upward right. But as you get closer here, you can see that it's starting to curve a little bit. And then it's going to cross that null line and go in towards some particular value. Same over here. As we get closer here, you can see that it comes in, it crosses that null line, and then it starts to approach some line over here. This, again, is not as savvy a tool as p-plane. And so I would recommend using a program like p-plane. And so let's pull p-plane up. Here is p-plane. Our equation is 3x minus 4y. And our y prime is x minus 2y. We can graph it. And then we can even click around to see what the curves are doing. And we can see exactly what we were seeing before. Now, one of our eigenvectors was 4, 1. And so if we click on the point, which would be at 4, 1, let's see, 4 and 1 will be right around here or so. Well, maybe not. 4, 1, it should be right around there. In theory, that should be our eigenvector, unless I did something wrong. I guess it does kind of look like it's approaching that value. And so the values from the top of it are coming from above. The values from below it are coming from below. And so, yeah, that is definitely going to be our eigenvector. Our other eigenvector was 1, 1. And so if we just choose this point up here at 5, 5, we can see that some are going down, some are going to the left. And so everything is escaping that. And that's really where the idea of chaos theory comes in. Note, if you are just a little bit below this value, the behavior is going to come down and then curve back. But if you are a little bit above, it's going to curve down and go in this negative y direction forever. That initial change, or that small change in your initial condition, is going to have a drastic effect on the long-term behavior. And that's what chaos theory is all about. a small change makes all the difference. That said, let's try another one. And so this one was a saddle point. Hopefully the next one will be something else. If it is a saddle point again, we might just call it at that point and try a different one. And so the next one, x dot y dot equals 3315. xy. And so with this one, we could do the exact same process. And so we can solve this. Let's start by doing a minus lambda I. So a minus lambda I in this case is going to be 3 minus lambda, 3, 1, and 5 minus lambda. And so our characteristic equation is lambda squared minus the trace plus the determinant. The determinant in this case would be 15, and then it's going to be minus 3, and so that's 12. Excellent. And so that factors nicely to be a lambda minus 6 and lambda minus 2. So lambda 1 is going to be equal to a, let's see, lambda 1 is equal to 6 and lambda 2 is equal to 2. And so at this point, we can classify it. Since both of the eigenvalues are positive, this is going to be a source or an unstable node. I'll put in parentheses, source. If I can spell source. There we go. Usually I just call it an unstable node because this is a node, it's a single point, which is having everything going away from it. And that makes it unstable. And so now let's find the eigenvectors, and then we will find the general solution and graph it. And so for eigenvalue 1, which is equal to 6, we are going to get 3 minus 6 is negative 3, positive 3, 1, and then 5 minus 6 is negative 1. And then it's xi equals 0, 0. That tells us that our first eigenvector is going to be 1, 1. For lambda 2 equals 2, we're going to have 3 minus 2 is 1, 3, 1, and 5 minus 2 is 3. This tells us that our second eigenvector is going to be equal to 3, negative 1. From this, we can find the general solution. The general solution is going to be given by x, y is equal to a e to the 6t times 1, 1 plus b e to the 2t times 3, negative 1. We can then graph this. And so let's do the phase diagram or phase portrait for this. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And so our first eigenvector is 1, 1, and that is going to be coming out at a 45-degree angle. And then our second one is 3, negative 1. So 3 in the x direction, negative 1 in the y direction. So it looks something like this. Now, this was our eigenvector 1. This is our eigenvector 2. Our first eigenvector and our second one are both going out. And so we know that it is coming out in all directions. But our first one is going much faster because of the 6 as the eigenvalue. And so I would usually represent this by putting a second arrow on that eigenvector. And so eigenvector 1 is going faster than eigenvector 2. And that makes it so that it's easier for me to graph this, because we know that it's going to be curving. And now we can say that it's going to be curving in the direction of eigenvalue 1, because it's going faster in that direction. And so it's going to be curving something like this. Note, it's not going to be curving back on itself. And so we wouldn't want it to look like this. That would be bad. It's still going to be going away from both eigenvectors. It's just going to be going away from this one much faster than this one. It's going to be going out in this direction much faster. And same in the other direction. And so down here, it'll be coming out in this way. There we go. And so that's what the phase diagram or phase portrait for this would look like. If we want, we can verify it. Let's see if we can put this one into p-plane. Probably won't put them all into p-plane, but it's good to verify at least a couple. Oh, and let's minimize this so that we can see it. And so we are dealing with 3x plus 3y. We are dealing with x plus 5y. We are graphing it, and we can see what the behavior looks like. And it is precisely the behavior we thought we were going to get. And so that's how we graphed that one. That was an unstable node. Let's try the next one and see if it is a stable node. And if we can get a stable node out of one of these, then we will move on to complex eigenvalues. Let's see. So for the next one, it is x dot y dot equals -3, 2 to -3 times xy. And so for this one, we can do the same process. We are going to get a lambda square, or let's do a minus lambda I first, which is -3 minus lambda, 2 and -3 minus lambda. And so our characteristic equation is lambda squared minus the trace, which is going to be a plus 6 lambda. And then it's going to be plus the determinant. And so that is going to be a -3, and -3 is +9. That's going to give us a 4. So this is going to be a +5. Excellent. So this factors nicely to be lambda plus 5, lambda plus 1. And so that tells us lambda 1 is going to be equal to -5. Lambda 2 is going to be equal to -1. And so we are in luck. This is a stable node. Also known as a sink. And the way that we know this, whoops, I had the share on the whole time. That's all right. You know the work at this point. And so, yes, we figured out a minus lambda I, and then we created the characteristic equation. And in doing the characteristic equation, we factored it. We got these two factors out of it. Since they are both negative, we know that it is going to be a stable node. At that point, we can find our eigenvectors. And so for lambda 1, which is equal to -5, we get -3 minus a -5. That's going to give us -3 plus 5, which is 2. -3 plus 5 is 2. xy. That tells us that our first eigenvector is going to be equal to 1, -1. Now we do the same. Eigenvalue 2 is equal to -1. And so at -1, we're going to be getting -3 minus -1 is -2. And so this is a very common set. Eigenvalue 2 is going to be 1, 1. These two eigenvectors are by far the most common when you're dealing with simple systems, mainly because the numbers just work out very nicely for them. But now we have a general solution. And so our general solution is going to be xy equals a e to the -5t, 1, -1, plus b e to the -t, 1, 1. We can now graph this. And so here's our Cartesian coordinate system. 1, 2, 3. We don't even care too much about them because we know we are going to be going at 45 and -45. And so eigenvalue 1 is -5, and it corresponds to this eigenvector. It is going in. All of them are going in. Eigenvector 2 corresponds to this vector. And the one which is going in faster is eigenvector 1 because of the -5. So again, I would usually represent this with a second arrow to show that it is going faster in that direction. Once you know it's going faster in that direction, we can do our curves just like we always do. As to how many phase lines to put in as many as you feel comfortable putting in. The important thing is that we know the behavior that is going on. So make sure you have every region covered at the very least. Phase lines should not cross. There we go. Maybe a couple in each region, just for good measure. And there we go. For a system of differential equations given by that, we get this, which is a stable node. It's not too bad. And so those are the 3 cases for real valued systems. The question becomes, what happens when we have complex values? And things get a little bit more problematic. Now, there's some additional problems in case you want to try them out. But complex valued eigenvalues, well, we haven't dealt too much with them, but they work very similar. And so recall that in a 2-dimensional case, formula for the characteristic equation is given by this quadratic. And while this equation will often have real values, frequently the solutions will give you complex conjugate solutions. The nice thing is it's always going to be conjugates. And so if you have a plus bi, the second solution is going to be a minus bi. Now, we can actually just solve this the same way, like the exact same way. The problem with that, though, is you get this expression. And this expression is a c1 e to the a plus bit and b c2 e to the a minus bit. Now, c1 and c2 will both have imaginary numbers in them. And so that makes it difficult. Drawing phase diagrams and finding real valued solutions while the system is written in this form is difficult. Thankfully, Euler's formula greatly simplifies this system. If you recall, e to the a plus bit is equal to e to the at cosine of bt plus I e to the at sine of bt. And that's something that you should have learned in trigonometry. I believe that's where we first explore complex numbers with exponentials involved. Another interesting thing is that since the eigenvalues are complex conjugates, it turns out that our eigenvectors will also be complex conjugates. Because of this symmetry, we have an interesting trick, which allows us to write out the solution to complex eigenvalue systems in terms of sine and cosine, using only a single eigenvalue and eigenvector. And so we're going to be able to take this equation, basically get rid of this second term, and write everything in terms of sines and cosines, where we have one which is a real part and one which is an imaginary part. And so consider this system. This is a nice little system. X dot y dot equals 3, -2, 4, -1, xy. When we solve this, we get the eigenvalues 1 plus or minus 2i. Now, we can use that eigenvalue and plug it in to find the eigenvector. When we plug it in and get the eigenvector, just the same way that we always have, we get this equation here. Now, it turns out these two rows, the first row and the second row, are going to be proportional to each other in much the same way that it is for real values. It's just harder to see because we have the complex numbers. You can use the first row or the second row to create an eigenvector. Choose whichever one is easiest. Depending on which one you choose, your final answer is going to look significantly different. But because we're talking about parametric curves, the answers are actually going to be the same. And that's something which is a little bit weird for folks at first. You might get answers which look significantly different, but are the exact same solution, depending on if you choose the first row or the second row. In this case, it looks like I have chosen to use the first row. And I got the eigenvector 1 and 1 minus I. So that's using the first row and the first eigenvector, the 1 plus 2i. Well, we can write the solution out in this format then. And so we know it's going to be complex conjugates. So it's going to be a times 1 over 1 minus I, e to the 1 plus 2it, plus b, 1 and 1 plus I, e to the 1 minus 2it. It's a terrible solution. And so let's clean it up. The way we're going to clean it up is by basically tossing out our second term. We're just going to look at the first term. And so the first term looks like this: a and then 1 minus I, e to the 1 plus 2it. We can rewrite this in terms of cosine and sine. And so we are going to get a times 1 over 1 minus I, e to the t, cosine of 2t plus I sine of 2t. Well, we can then bring this into, or we can then distribute everything in and get a little bit of a mess. Notice this does turn into a little bit of a mess. But we can break it apart so that we have a real component and an imaginary component. Our real component is going to have the cosine of 2t, and then the cosine of 2t and the sine of 2t. Our imaginary component is going to have the I sine of 2t, then the I sine of 2t, and the I cosine of 2t term. Well, if we did the conjugate, we would just get the exact same thing. And that's where we can do a little bit of magic. We can essentially break this real part and this imaginary part and make it so that the real part has the A term and the imaginary part has the B term. And so get rid of the AI and rewrite it as B. This new solution is the actual solution for the problem. And the proof is right here. Basically, we can redefine what our two terms are. So A will now be A plus B, and B will be A minus B times I. But from the one term here, A times 1 minus I, e to the 1 plus 2it, we're able to get the two components of it. And we will have it where it is this one, which is dealing with the cosine of 2t, cosine 2t plus sine of 2t, the real component of it. And then this term, which was the imaginary component of it. But the imaginary number I just gets absorbed by the b. And so we don't have to worry about it anymore. This is now the general solution for the problem. As always, we can find a particular solution if we're given information. Usually that's a little bit trickier, but it's not that bad. It's really the same process as before. You'll just have some trigonometric functions to play with. And so here is the strategy. To solve a homogeneous linear differential system of differential equations, just like before, you find the eigenvalues, and then you find an eigenvector for one of your eigenvalues. Simplify the expression c e to the lambda t using Euler's formula, and rewrite it as the sum of real and imaginary parts. And so your simplified expression should look like e to the at, and then a vector with trig components, and then I e to the at, and then another vector with trig components. Once we do that, we bring the coefficients back in. And so we will have a times this first term and b times this second term, and that will be your general solution. Let's try it out. And so for this first one, x dot y dot equals -1, -4, 1, -1. And then we will have the x, y. And so in order to solve this one, it's going to be the same process as we've done before. We're going to figure out what a minus lambda I is. So a minus lambda I is going to be equal to -1 minus lambda, -4, 1, and -1 minus lambda. So now we need to do our characteristic equation, which is lambda squared minus the trace gives us a +2 lambda, and then plus the determinant, which is 1, and then it's going to be +4, so that is +5. Solving this, we're going to get a lambda squared plus 2 lambda plus 1 equals -4. And so that's telling us that we're going to have two eigenvalues. Lambda 1, well, let's show the rest of this. It'll be lambda plus 1 squared equals -4. We square root both sides. And that tells us that lambda 1, or I guess we could just go lambda in this case, is going to be equal to -1 plus or minus 2i. And again, I forgot to stop the share. Apologies for that. And so we just did the algebra here. And so we created the equation, or the matrix. We created the characteristic equation. We solved the characteristic equation, and we got our two solutions. Lambda equals -1 plus or minus 2i. And we could have written this as lambda 1 and lambda 2, but remember, we're only going to need one of them because we're going to create an eigenvector for one of these, and then we're going to use it to figure out the general solution. Typically, it's a good idea to use the positive one just for consistency's sake. And so let's let lambda 1 be equal to -1 plus 2i. Well, now finding our eigenvector, we need to plug that in. And so we are going to get -1 minus -1 plus 2i. Then it'll be a -4 and a 1 and a -1 minus -1 plus 2i. This times xy equals 0, 0. Cleaning this up, the -1s actually cancel. So you're going to get 2i, -2i, then -4, and then it'll be a 1, and it'll be a -2i. Now, it might not look like it, but these two rows are proportional, just like it is for all of the other eigenvector problems we do. And so we can choose either row to figure out our eigenvector. I would probably go with the second one, just because it looks the cleanest. And so that would give us a 2i and a 1. If we want to verify that this works, we could multiply it by the top. 2i and a negative 2i is going to give us a negative 4i squared, which is positive 4. And then 4 plus negative 4 gives us the 0. And so now we know that we're going to have terms of this form. And I'll even just write it down here real quick. X, y, and I'm just going to put a little asterisk here because this is not the actual solution. It's going to be equal to AE to the negative 1 plus 2i t times 2i and 1. And of course, the complex conjugate will be the b term, but we don't care about the b term because now we're going to take this solution, and we can even drop the a, and we're just going to write this out in terms of sines and cosines. And so writing this in terms of sines and cosines, we have e to the negative t, because distributing that, we get the negative t, times 2i and 1. And then it's going to be times cosine of 2t plus I, e to the negative t still, times this vector again, times sine of 2t. And so this is the e to the a plus bi. Well, the b term comes in here, and then we have the I sine of 2t. Now we want to break this apart so that we have the real components and we have the complex components. If you want, you can multiply the cosine in first and multiply the sine in first, if that helps you. You don't have to, though. And so let's just look at this and go straight to the real components. And so for the real components, on the top, 2i and cosine, that's going to be a negative, that's going to be an imaginary component. Here we have an I and an I gives an I squared. So that's going to give us a negative 2 sine of 2t. On the bottom, we have a 1 cosine of 2t. That is a real component. And that is the last real component because the other one is going to be an I times 1 times sine of 2t. Now for the imaginary component. And so the 2i cosine of 2t, well, that's imaginary. So we're going to say that this is 2 cosine of 2t. Same with this one on the top. We have an I and an I. That's an I squared, so that goes to real. On the bottom, 1 times cosine, that's real. Here, I times 1 times sine, that is imaginary. And note, the I is already out, so we don't have to bring it back in. At this point, we're one step away from the general solution. All we have to do is bring our coefficients back in. And so our final solution for this is going to be x, y equals a e to the negative t times negative 2 sine of 2t cosine of 2t plus b e to the negative t 2 cosine of 2t sine of 2t. And that's how we solve these when we have complex eigenvalues. It's pretty much always going to be the same process, which is the good news. Whether it's, I guess I'll save that for the next bit. because the next bit is going to be determining the stability of these. And so much like with the real values, we could do another example, but we're going to have to come back and do these again once we're doing the graphs. And so let's go straight to the graphs. When we are classifying these, it turns out there are 3 different classifications, but there's also 3 different directions that the 2 different directions the spirals could be going, clockwise or counterclockwise. So unlike real valued eigenvalue problems, drawing good sketches for complex functions is often challenging. Typically, the graph will either be a spiral or an ellipse, but in both cases, one dimension will typically be longer than the other. Getting good at drawing these is a challenge, and so provided you can determine the case you are in and the direction that the system is moving, I will be content. I'm not looking for perfect graphs on these spirals because that can be difficult. You need to take into consideration the eigenvalues, the eigenvectors, as well as the null lines in order to get very good with these. And you also have to be able to consider the individual elements of your system. That said, here is how we can classify them. And so provided our eigenvalues have an imaginary part, there are 3 main cases we will encounter. An unstable spiral. In this case, the real part of the eigenvalue is positive. A stable spiral. In this case, the real part of the eigenvalue is negative. And the last one is a center. In this case, the real part of the eigenvalue is 0. To determine whether or not it is spiraling clockwise or counterclockwise, we actually can just look at a single term here, and that is the B value. If this B value that you have in your matrix, and so the first row, second column value, if that is positive, the system is moving clockwise. If it's negative, the system is moving counterclockwise. And this works for spirals or centers. With that, we get 6 different graphs. And so we could have an unstable spiral where it is spiraling clockwise. This is unstable and it is spiraling counterclockwise. And you can see the arrows, they are pointing that it is going in this direction. And so this is an unstable spiral. Because the real part of our eigenvalue is positive, we know the graph is spiraling outward. Because the B value is negative, we know that it is spiraling counterclockwise. Here is another unstable spiral, but this time it is going to be spiraling in a clockwise direction because the 10 value is positive. Here is a stable spiral. And so now things are spiraling inward. And we can tell from the original problem because the eigenvalues have a negative value there. And so the real part of the eigenvalue is negative. That tells us that it is spiraling inward. Because it is a negative 10 there, that tells us that it is going to be going counterclockwise. This is the same problem, but now it is a positive 10 value. And so that tells us that it is going to be spiraling clockwise. The eigenvalue still has a negative component, so it is still going to be, this should be saying stable. Yeah, gotta love it when there's a typo in the notes. This is a stable spiral because we have the negative value there. And so that tells us we are having a stable spiral, which is spiraling clockwise. Case 3 is a center. This one is not spiraling inward or outward. Instead, we're going to be getting concentric ellipses. And so in this case, we have the real part is 0. If the real part is 0, we are going to have it spiraling, or not spiraling, just circling around the origin in an elliptical motion. Because the B value here is negative, we know that it is going to be going in a counterclockwise direction. For this one, it is going in a clockwise direction because that value is a positive 10. And so here are some practice problems. Before we do those, let's look at the one that we just did. And so looking at this, we can see that we have a negative real part. Because we have a negative real part in our eigenvalue, we can classify this as a stable spiral. For the graphs of this, I'm not going to be looking for a tremendous amount. I just want to see that you understand how it is spiraling. And so you can just create an arbitrary axis here. Usually I do the 1, 1 and the negative 1, 1. We'll just pretend that those are our nullines. If you want, you can actually find the nullines and plot those out, but I'm not going to ask you to. And then we know that this is going to be a stable spiral, so things are going to be spiraling towards the center. Because this value here is a -4, we'll bring that so we can see the -4 there. That tells us that we are going to be going in a counterclockwise direction. And so we're going to be going in a counterclockwise direction as we spiral towards the center. And so if we were to do this from here, we could say it's going to be spiraling. And this is not a good graph at all, but that is okay. We are not looking for perfection on these graphs. We have enough to worry about with all of the other stuff that we are doing in this class. And so this would be more than sufficient for our purposes. If we want, we can actually get the official graph by using p-plane. And so let's pull p-plane up real quick. Here we go. Oh, and let's just minimize this. And we will say our p-plane, our function is -x minus 4y. And our other one is going to be x minus y. And we can see that we were right on some of it. And so this is going to be definitely spiraling inward. And so it is a stable spiral. As we can see, it is spiraling in a counterclockwise direction. So it is spiraling in this direction. If we wanted to, again, we could do the nullines. And seeing the nullines will make it so that it's easier to graph this. Because remember, the nullines are going to tell you when it's going to be going in an upward or downward direction. And we can break the graph up like that to do a much better graph. For our purposes, what we did is more than sufficient. So that one that we just did was a stable spiral. Let's see if we can find a unstable spiral, and then let's see if we can find a center. If we can find those two, then we will be content with these, and we'll move on to the next section. And so that was a stable spiral. Let's do number 1 here, because that looks like it's going to be a center. And so x dot y dot equals 1, 2, -5, -1, xy. And so we're going to do the exact same process. And this time, I'm going to stop the share so that we can actually see it. We're going to start by doing a minus lambda I. Which will give us a 1 minus lambda, a 2, a -5, and a -1 minus lambda, xy. And we're going, we don't need that quite yet. That'll be a little later. And so now we're going to find the characteristic equation, which is lambda squared minus the trace. Well, the trace in this case is 0. And then it's going to be plus the determinant. So the determinant is going to be a -1, and then it's going to be plus 10. So that's going to be plus 9. That gives us a lambda equal to plus or minus 3i. Because the real component is 0, we know that this is going to be a center. And so now we find our eigenvector. And so again, let's use the positive 3i value. If you use the negative one, some weird stuff can happen because you have to take that negative sign into consideration when you're doing your e to the a plus bi. It'll become an e to the a minus bi, which will mean that you'll have to change the signs on your sign and it could just get messy. So always choose the positive one. And so for lambda equal to positive 3i, we end up getting 1 minus a 3i, a 2, a negative 5, and a negative 1 minus 3i times xy equals 0, 0. And so again, you can choose the top row or the bottom row. It does not matter. I'll use the top row because the numbers look a little smaller. And we will get our eigenvector as being equal to a negative 2 and then a 1 minus 3i. If we want, we can verify that this works by multiplying it by the bottom row. I'm willing to just take it that it works and call it good there. And so now we have our term, and it's going to be that xy, again, I'll put a little asterisk here, is equal to a e to the 3i, and that is going to be a negative 2, 1 minus 3i. Well, now we need to turn this into sines and cosines. Because there is no real component, though, we can actually just get rid of the e term in the front. And so this is going to be equal to a negative 2, a 1 minus 3i, times cosine of 3t. Oh, and I dropped the t there. There should be a t there. There we go. Plus I, negative 2, 1 minus 3i. And then it's going to be a sine of 3t. Well, now we need to break this into the real and imaginary parts. And there are multiple ways we can do this. I usually just go one term at a time, real and imaginary. And so looking at this, we have the negative 2 cosine of 3t. That is a real term. The I negative 2 sine of 3t, that's imaginary. The 1 cosine of 3t, that is going to be a real term. The 3i times that is going to be imaginary. The I times 1 times sine of 3t is imaginary. The I times negative 3i is going to give a plus 3 sine of 3t. Now we're going to have an I and our imaginary parts. And so our imaginary parts, we are going to have a negative 2 sine of 3t. We're going to have a negative 3i, so negative 3 cosine of 3t. And then we're going to have a 1 sine of 3t. Running out of room there, but that's okay, because now we have our solution. So xy is going to be equal to a. We no longer have the exponential term, and that's going to be the case whenever we have a center. And it's going to be our negative 2 cosine of 3t, then cosine of 3t plus 3 sine of 3t, plus b, then it is a negative 2 sine of 3t and negative 3 cosine of 3t plus sine of 3t. Excellent. Our last step, we want to graph this thing. We don't have to do too specific of a graph, but we should figure out if it's going clockwise or counterclockwise, and then make sure that we draw it out as a center. And so in this case, because it is a 2 in the first row, second column, that tells us that we are going to be going clockwise. And it is a center, which means that we are going to get concentric ellipses going in a clockwise direction. The tilt, you could do whatever tilt you wanted. Again, you can get more precise using the null lines, but I'm not going to hold you to that. And then these are going to be going in a clockwise direction because the 2 was a positive value. And so there's that solution. If we want, we can check. And so let's check using our good friend p-plane. Using p-plane, this was x, and then it was a plus 2t. Or sorry, x plus 2y, I should say. And then it was a negative 5x minus y. Graph it. It's showing the null lines for us. And we can see the direction that it's going. And so it is going to be going in a clockwise direction, and it is definitely a center. It's not spiraling inward or outward. Excellent. And so let's do one more. Let's see if we can figure out one which is going to be, what was it? We've had a stable spiral, and so now let's see if we can find an unstable spiral. Actually, we'll just take the next one, and whatever we get, we get. Let's see. All of these should be fairly similar. Eyeballing it, number 4, since it has the 9 and negative 9, we know that that term is going to add to give 0. And so that's going to give us a center, since we are aware that this is going to be a complex eigenvalue problem. And the trace is always going to tell you whether or not it's going to be stable or unstable. If the trace is positive, such as this one, we have a 7 minus 3. That means we're going to get a lambda minus 4 term, which will then go positive. And so this should be a unstable spiral. Let's try this one. Do an unstable spiral. I don't remember if the first one we did was stable or unstable, but this looks like a good one. X dot y dot equals 7, negative 10, 10, negative 3, x, y. Excellent. And so to do this problem, it is the exact same process that we have done with everything so far. And so we will say that our a minus lambda I is equal to 7 minus lambda. I want to make sure that I wrote that down right. Seeing 2 10s there, that's always surprising. But nope, that's correct. 7 minus lambda, negative 10, 10 and negative 3 minus lambda. The reason why it's important to write it down right is because if there's a small error, the problem can get monumentally difficult. And so from here, we know it's going to be lambda squared minus the trace, which is going to be a 4 lambda, and then it's plus the determinant. So 7 and that is going to give a 20. Negative 21. And then it's going to be minus a negative 100. And so that is going to give us a total of, oh goodness, I do not like this problem, 79. And so we are going to get a plus 79 here. That's concerning. Let's see what we get from that. When we continue this problem, my guess is I made a mistake when I was coming up with this problem, and it ended up making it much, much harder than I wanted it to be. But just verifying that real quick, we have the negative 21. We are going to have a positive 100. That gives a 79. Gross. All right. And so using completing the square, we're going to get lambda squared minus 4 lambda plus 4. And then we're going to move the 79 over and get a negative 79 plus 4, which is negative 75. And so that means that lambda is going to be equal to negative 2 plus or minus 3, or sorry, positive 2 plus or minus these 5 times the square root of 3. That is not pleasant at all. That said, maybe it's good to do one which is not pleasant. And so when we go through this process, it's going to be the same. You verify one final time that I copied it down, right? I did. I must have just been in a bad mood when I came up with this problem. So for lambda 1 equal to 2 plus 5 square root of 3, we are going to get the matrix 7 minus a 2 plus 5 root 3, a negative 10, a positive 10, and then a negative 3 plus 5, or sorry, minus a 2 plus 5 root 3. xy equals 0, 0. We can clean this up a little bit. And so cleaning this up, we can do the 7 minus 2 is going to give a 5. Plus 5 root 3 becomes a minus 5 root 3. Then a negative 10, and then a 10, and negative 3, negative 2 is going to give a negative 5 minus 5 root 3. And so we can choose our eigenvector from this. So let's let our eigenvector be given by about the first row. And so that'll be a 10 and a 5 minus 5 root 3. That tells us that we're going to be dealing with terms of the form e to the 2 plus 5 root 3 t, and then a 10 and a 5 minus 5 root 3. Well, now, just like before, we need to break this up into the sine and cosine components, which isn't going to be terrible. It's just going to be messy because we're going to have a root 3 floating around everywhere. And so to do this problem, we would say that we are going to have e to the 2t. Then it's going to be a 10. Oh, I'm sorry. There should be an I in here. Always be careful when you're doing this stuff because it is so easy to make a mistake. There we go. That's much worse. And so it's going to be a 10, and it is going to be a 5 minus 5 root 3 I cosine of 5 root 3 I, or sorry, 5 root 3 t plus I e to the 2t, 10, and then a 5 minus 5 root 3 I sine of 5 root 3 t. That is not very pleasant. Now we can continue it. We are going to have the real components and the imaginary components. So we will have the e to the 2t. For our real components, we will do a 10 cosine of 5 root 3 t. And then we will get the 5 and the cosine again. So 5 cosine of 5 root 3 t. And then for this one, it will be the I times I is I squared. So negative and negative makes it a plus 5 root 3 sine of 5 root 3 t plus, and then we're going to have our imaginary part, e to the 2t. And then it's going to be, the imaginary part on the top is just going to be the 10 sine term, sine of 5 root 3 t. On the bottom, we're going to have the cosine term here, a negative 5 root 3 cosine of 5 root 3 t. And then on this side, we're going to have the 5 sine term, 5 root 3 t. And the good news is that's the bulk of the work done there. Now we just have to put our coefficients in. Now there is a sly way to cheat at this point, which I will do. The sly way to cheat is we can say that xy is equal to a times this first one plus b times the second one. And we don't have to rewrite the problem because I don't know about you, but I'm tired of seeing the 5 root 3. But that's the general solution for this one, unless I made a typo somewhere, which would really break my heart because that was a lot of messiness. The good news is that in spite of whatever this mess ended up being, we can still classify it and graph it very quickly. To classify this, we see that we have a positive 2 here, and it is complex. And so that means that we are going to have an unstable spiral. Because it is a negative 10 up there, that tells us that we are going to be spiraling in a counterclockwise direction. And so the graph of this is going to be spiraling outward in a counterclockwise direction. And you can graph it as best you can. Again, I will not be concerned with the direction now, or with how tweaked it is, where your null lines are drawn. I just want to see that you have the general idea that it is an unstable spiral, meaning it is going in an outward direction, and that it is going in a counterclockwise direction. That one was definitely a bit more work than I anticipated, but it's good to see ones like that every now and again. And so that is the real and the complex case. This is all just the linear case, though. What do we do when we are dealing with something which is nonlinear? And we've dealt with nonlinear stuff before, and so that's the good news. Chapter 7 dealt with the nonlinear stuff. We can use null lines to figure out what's going on. The problem is the null lines won't tell the whole story. Sometimes they will tell you exactly what's going on at the equilibrium points, but not always. And if we want to figure out exactly what's happening at those equilibriums, the way to do it is to find the Jacobian. And so the Jacobian is a linearization at those points. And so suppose that we have this example here. X prime is equal to 1 minus x, y prime is equal to y squared minus 1. We can graph this using the chapter 7 methods. Using null lines, we can graph it fairly quickly. But we can also find the equilibriums, which will be at 1, negative 1, and 1, 1. Eyeballing it, it looks like this value here is going to be a saddle point, and it looks like the one down here is going to be a stable node. We won't always be able to tell that just based on the null clines alone, though. In this case, we probably could. But if we can't, we can use the Jacobian matrix, which is a linearization at that point. And so suppose that you are given functions, x prime of t equals f of xy, and y prime of t is equal to g of xy. The Jacobian matrix is the matrix of partial derivatives, in which we have the partial of f with respect to x, then partial of f with respect to y, then partial of g with respect to x, and partial of g with respect to y. This will give you a linearization of the system. And when we evaluate it at the critical points or at the equilibrium values, it's going to give us a system which is a homogeneous autonomous system, and we can do the exact same eigenvalue analysis that we were just doing to determine the stability of it. And so for the example problem that we had above, 1 minus x and y squared minus 1, the Jacobian of this, the partial with respect to x, is -1. The partial with respect to y is 0. And for the second equation, the partial with respect to x is 0, and the partial with respect to y is 2y. Evaluating it at the 2 points, 1, 1, and 1, -1 and 1, 1, we get eigenvalues, which are -1 and -2, telling us that we are going to have a stable node. And then at 1, 1, we have -1, 2, which tells us we are going to have a saddle point. And so we have a stable node and an unstable saddle point. That's how we're going to be evaluating these things. And so whenever we have a nonlinear system, if we're not sure the stability of a point, we can use the Jacobian to figure it out. Now I have a bunch of practice problems. We might do one real valued and one complex valued and see what we get. But it should go fairly painlessly. So let's try the first problem there. And so x dot equals x squared minus x, and y dot equals y squared minus 1. Let's see if we can find the equilibrium values, classify the equilibrium values, and then we're going to see if we can graph the phase portrait. And so x squared minus x and y squared minus 1. To begin with, let's see if we can find the equilibrium values. And so x squared minus x, if we set that equal to 0, which is how we find the equilibrium, we're going to get that x is equal to 0 or x is equal to 1. For this one, we're going to get that y is equal to -1 or y is equal to +1. That tells us that we're going to have 4 equilibrium points. We're going to have the point 0, -1. We're going to have the point 0, +1. We're going to have the point 1, -1. We're going to have the point 1, 1. To classify all of these, we're going to need to find the Jacobian, which is the matrix of partial derivatives, and then we're going to need to evaluate the Jacobian. And so the Jacobian, J, is the matrix of partial derivatives. The partial with respect to x of the first equation is going to be 2x minus 1. The partial with respect to y of the first equation is 0. For the second equation, the partial with respect to x is 0. And the partial with respect to y is going to be equal to a 2y. And so now we need to evaluate it at all of these points. And when we evaluate it, we'll find the eigenvalues, and that will tell us whether or not it is stable, unstable, a saddle, or if it's one of the complex cases. In this case, it's going to be real valued. And one of the nice things is this is a diagonal matrix. Whenever you have a diagonal matrix, the values on the diagonal are your eigenvalues. And so that's going to make this one much nicer. And so for the first point at, let's say, 0, -1, we are going to be having the Jacobian be 2 times 0 minus 1 is -1, 0, 0, and then a 2 times -1 is -2. Our eigenvalue 1 is -1. Our eigenvalue 2 is -2. That tells us that this is going to be a stable node. Because both eigenvalues are negative. Note, this trick for the eigenvalues only works when you have a diagonal matrix. If we didn't have a diagonal matrix, we would have to go through the standard characteristic equation in order to determine what the eigenvalues are. At the next one, 0, 1. Same process. And so now we're going to get a -1, 0, 0, and it's going to be a, something looks off. Let me pause the video for a minute and see if I can figure out where I made my mistake, if I made a mistake. Good news, I didn't make a mistake. I am just bad at doing computations after doing a couple hours of computations. It's 2 times 1, not 2 times 0. And so that's going to give us a 2 there, which tells us that eigenvalue 1 is equal to -1, eigenvalue 2 is equal to 2, and so this is going to be a saddle point. Now we do the next one. At 1, -1, we're going to be doing 2 times 1 minus 1 is a +1, 0, 0, -2. Since we have a lambda 1, which is a +1, and lambda 2, which is a -2, this is going to be a saddle point again. We'll see if we can squeeze our last one in here at the point 1, 1. Our vector, or our matrix, is going to be given by 1 and a +2. So our eigenvalues are going to be equal to 1 and 2, which tells us that this is an unstable node. Note, when we're doing this, we're not really caring too much about the eigenvectors, just the eigenvalues. And so it can go fairly quick to figure out those classifications. Once we have this, we can actually create the phase diagram without too much trouble. So let's see if we can create the phase diagram. Let's see. We will create a Cartesian coordinate system. Doesn't have to go out too far. We'll go about 3 in each direction. And then we'll just use the techniques from chapter 7, where we're using the null lines. And so our null lines are given up here. We have x equals 0, which would be a vertical line going right up there. We have x equals 1. We then have y equals -1 and y equals +1. Probably should have done that one in a different color, but that is okay. We now have a number of different regions which we need to figure things out in. In fact, we have 9 different regions. We want to figure out the directionality in each one of those. And so looking at the first set, we've broken things based on x equals 0 and x equals 1. If we are to the right of x equals 1, we are going to have a positive x prime. If we are in between 0 and 1, it is going to be negative. And if we are beyond that, we are going to be going to the right again. For the second equation, to determine the directionality in the y direction, it's broken up by y equals -1 and y equals +1. If we are at a very large value, a large positive value, it's going to be positive. If we are between -1 and +1, we know we are going to be going in a negative direction. And if we are at a large negative value, it's going to be positive again. We have 4 equilibriums. And we know that the 0, -1, 1, so 0, -1, this one is going to be a stable node. This one up here is going to be an unstable node, and the other two are going to be saddles. And at that point, we can use our arrows and our equilibrium to figure out what the graph is going to look like. And so we are going to get curves which are going to be coming in an upward direction and coming out this way. We're going to have them coming up in this direction and going towards this value. We might have some that curve like this and still go towards it though. Up here, well, we're not 100% sure what it's going to look like, but it'll generally be coming in this direction. Over here, we know we're going to have curves coming up in this direction. We know that we are going to have curves in the central part here, which are going to be coming from this top bit, and it's going to come down. Up here, we are going to have things which are going in an up and to the left direction. So we'll have things looking like this and possibly like this. Up here, everything's going up and to the right. We're not 100% sure about the directionality there. And so we'll do something like that. And we're going to have stuff down here going down and to the right. And so it'll look something like this, or possibly like this, all depending on where you're starting at. And then in the central, we'll have stuff coming down here and curving like this and curving like this. Add some arrows just for good measure. And this is what our graph is going to look like. That is quite the phase diagram. Let's see how accurate we were using the program p-plane. And so pulling up p-plane, this equation that we just dealt with was x squared minus x and y squared minus 1. And sure enough, our graph is going to look pretty similar. It's a little bit off in some areas as far as how it's escaping certain values. But on the whole, it's fairly accurate. Excellent. And so there's how we do the phase diagram, where we can now include the stability of the equilibrium points. Let's do one more example. This time we'll do one which is going to have a complex value. Notice I have a couple of models here as well. The values for those models make them a little bit messier to do by hand. And so you might want to give them a shot if you really feel up to it. If not, that's okay. But let's try number 4 down here. I attempted that one before I began recording, and I made a typo in it, which made it so that my eigenvalues were very wrong, and it was very heartbreaking. And so I would like to have a redemption shot at this one. Let's see if I can get it right this time. And so x prime is equal to y squared minus 4, and y prime is equal to x squared minus y squared. Let's see if we can do this one. I think this might be the last computational problem we'll do today. Then we'll just be exploring a few models. All right, and so y squared minus 4 and x squared minus y squared. Our first step is to find the nullclines so that we can figure out where the equilibrium values are going to be. For our first one, it is going to be y equals 2 and y equals negative 2. Again, that comes from just setting the equation equal to 0. And then for the second one, it's going to be y equals x and y equals negative x. Now this is going to give us 4 equilibrium points because y is either positive or negative 2 and x is positive or negative y. And so our 4 equilibrium points are going to be at negative 2, negative 2, negative 2, positive 2, then a negative or a positive 2, negative 2, and a positive 2, positive 2. Our Jacobian, in this case, it's going to be a little bit more interesting. We're actually going to have to calculate some eigenvalues. The Jacobian is going to be 0. Then it's going to be a 2y. Then it is going to be a 2x and a negative 2y. When I did this problem before I recorded, I missed that minus sign. That threw the entire problem off. All of my stability was wrong. The phase portrait I did was bad. And so hopefully I got it right this time. If I didn't, I might cry after this recording. Yes. And so let's try this one now. And so we need to evaluate the Jacobian at all of the points. And so at negative 2, negative 2, we are going to be having, let's see, the Jacobian will be 0. It'll be negative 4, negative 4, positive 4. And so using our characteristic equation, we get lambda squared minus the trace, which is 4 lambda, and then plus the determinant, which is a negative 16. We can solve this. This is going to give us a lambda squared minus 4 lambda and then plus 4 equals a 16 plus 4 is 20. And so that tells us that our lambda is going to be equal to a 2 plus or minus the square root of 20. Note I used completing the square there. Completing the square is a very nice, quick way to solve these things instead of using the quadratic formula. And so I would recommend using completing the square whenever possible. Now, 2 plus or minus the square root of 20, we know that this is real because square root of 20 is a number. It's not a complex number. It's not an imaginary number. So the question is, are these values going to be positive or negative? And square root of 20 is more than 2. Square root of 20 would be 2 times the square root of 5. So 2 plus 2 root 5 is positive. 2 minus 2 root 5 is negative. This is going to be a saddle point. Now we do the next one. And so at the point negative 2, 2, we do the same process. And so at negative 2, 2, we're going to have 0. We're going to have 2 times 2 is 4. We're going to have a negative 4. And then we're going to have a negative 4. And so double checking that, the 2 and that, yes. And so we're going to get lambda squared minus the trace, which would now give us a plus 4 lambda. And then it's going to be minus the determinant, which is going to be a plus 16. In this case, we're going to get a lambda squared plus 4 lambda plus 4 is equal to negative 12. That tells us that lambda is going to be equal to a negative 2 plus or minus the square root of negative 12. Square root of negative 12 is going to make this complex. The negative 2 is going to make it so that this is a stable spiral. I'll underline these just to make it a little bit clearer where we're at. And so we got this one is a saddle point. This one is a stable spiral. For our next one, at the point 2, negative 2, we are going to have, again, 0. We're going to have 2 times y, so 2 times negative 2 is negative 4. We're going to get 2x, which is a positive 4. And then we're going to get negative 2 times negative 2, which is positive 4. So our characteristic equation, similar numbers, lambda squared minus 4 lambda, and now it is going to be a plus 16 again. That is going to give a lambda squared minus 4 lambda plus 4 equals, we'll have a negative 16 plus 4 is negative 12. Tells us our lambda is equal to a positive 2 plus or minus square root of negative 12. And so this one now, this one's going to be complex again, but because it is a positive real part, it is an unstable spiral. One more point, and I think I can fit it down here. So at the point 2, 2, we are going to have 0, 4, 4, negative 4. That's going to give us a lambda squared. It is going to be a minus the trace, so plus 4 lambda minus 16 equals 0. Because it's a minus, we know that this is going to be a saddle point right off the bat. But if we want, we can calculate it real quick. It's lambda squared plus 4 lambda plus 4 equals 20. And so lambda is equal to negative 2 plus or minus the square root of 20, which is a saddle. Much like the first one was, because square root of 20 is more than 2. And so we now have all of our classifications. Let's see if we can graph this. So to do the phase diagram, it's going to be the same process as before. Let's go out 1, 2, 3, 4 in each direction as best we can. And then we're going to do our nullclines. And so our nullclines, for our x nullclines, it's going to be y equals 2 and y equals -2. And I'll switch colors this time. For our y nullclines, it's going to be y equals x and y equals -x. Where these nullclines cross is at 4 points. And we've already found those 4 points. Note, the 0, 0 is not a equilibrium because that's just the y nullcline crossing itself. And so that really doesn't count as anything. And so now we can figure out what's happening in all of the different regions. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different regions. Let's figure out what's happening in the x direction first. And so in the x direction, if we are above this line, let's see. Yes, and so if we are above this line, then we know in the x direction, we are going to be going positive. And so that means that we will be going in this direction. And along this nullcline, we will also be going strictly positive. Below that, we're going to be going in the negative x direction. Negative direction, negative direction, negative direction, and negative direction. Below that, we are going to be going positive again. Doing the same on the other side, the y direction. If we are up here at a point where, let's say, x is 0 and y is a positive value, then we are going to be going in a negative direction. Because looking at this, if x is positive and y is, or sorry, if x is 0 and y is anything, it's going to be negative. And so that means in this region up here, it's going to be negative. It'll switch to positive as we are on the sides. And positive and positive. And then down below, it will go negative again. And I believe that is the directionality on all of them. And so where the Jacobian becomes important is in a case like this. And so we can see that we have saddle points at 2 of them. At -2, -2, and at +2, +2, we are going to have a saddle point. And we could probably determine that just from the curves themselves. But when we look up here at -2, +2, and over here at +2, -2, we can see that things are spiraling. It's going downward, and then it's crossing, then it's going upward, and then it's going to the left, and then it's going down. But what's not clear just from the nullclines is which one is a stable and which one is an unstable spiral. When I did this problem before I started recording, I had the sign wrong here, and I got the two mixed up, and it messed everything up horribly. But now we can tell that the unstable spiral is going to be at 2, -2. And so at this point, things are going to be spiraling outward. At this point, at -2, 2, it's a stable spiral. And so things are going to be spiraling into this one. And we can use that to graph. And so let's see if we can figure out what's going with our arrows. So at this point, we know it's an unstable spiral. And so things are going to be spiraling outward. And so it's spiraling up and to the left. It crosses this, starts to go down and to the left. It crosses this, it goes down and to the right. It crosses this, it goes up and to the left. Crosses this, it goes up and to the left. And then, well, let's see, either going to go up and hit this, or it's going to hit this, or it's going to hit this. This one looks like it's going to hit around here. And then it's going to start to go down and to the left. It's going to cross this, and it's going to come up and to the right. And once it hits that, it goes up and to the right. And note, we said that this one is going to be a stable spiral. And so that means that it is going to be coming towards this value. And then down and to the left and cross, and there we go. This is the shape that a lot of things are going to be taking. It's going to go from one towards the other. Let's do another trajectory. And so let's say that we start a little further out. We're going to be going up, and then we're going to be hitting this, and we're going to go down. And then we're going to come down. We're going to go down this way. And really, at this point, it just becomes more art than anything else. We might hit this one and go up and cross this, at which point it's going to be going up and to the right. If we're coming from here, we might cross this, go downward, and we're either going to cross this value down here, in which case we will always come down and start spiraling in here, or we might come down and continue on until we cross this value over here, which might be a little further out actually. Might be coming in like this, cross this, and then start to go up and to the right. Or it might come down here, cross this, and then again come down in this direction. Or down here, we might be coming, or let's see, this is always going to be going down this way. And so we might have a trajectory that comes from here and then crosses this one. Oh, shouldn't cross that line. If we cross this line here, for instance, we could then start to go down and cross this. And if we cross this, then we're going to be going up and to the left. If we're starting here, we could come up and hit this one, in which case we're going to spiral down this way, or we could come up and hit this one, in which case we're going to go this way. And at that point, we have a pretty good idea for what the phase diagram for this is going to look like. We can see that things are starting to spiral a bit. Generally, things are going to be spiraling from one of these towards the other one. Some of the specific curves might not be as smooth on this graph as they are in actuality, but we can clearly see that this is an unstable node. This is a stable node, or sorry, an unstable spiral. This is a stable spiral. And then both of these are going to be saddles. And without doing the Jacobian, figuring out which one of these was going to which one might have been a little bit trickier. And so it's nice to have the Jacobian to clarify that for us. Let's see what this one would actually look like using p-plane. And so using p-plane, the equation was y squared minus 4 and x squared minus y squared. And Norton is telling me stuff, which I don't need to know. And let's graph this phase diagram. And so there are the null lines, which we had. We can choose some points. And it becomes fairly clear what's going on just by choosing a few points around each of these. And so looking at this, our graph was fairly similar. We had things spiraling out from this point, and they were coming outward, and they're then approaching this other one. If things are spiraling a little bit more, then it might go out to this one, then it'll go up and to the right. Values are coming from the bottom left, and they're either going up towards this spiral, or they're going down and around and likely avoiding all of the spirals altogether. And so this gives us the behavior of this system. And so that's what we can expect with problems like this, nonlinear systems. We can use the null-clines to get us pretty far, but in the end, using the Jacobian is going to make it much, much better to visualize these things. That said, let's finish off by talking about some actual models. And we're not going to do any more computations with them. Instead, we're just going to try and make sure that we understand these models. We've spent so much of the semester trying to understand how to do systems of differential equations, and everything's really built up to this chapter. But when we think about these systems, what do they actually look like? And we have a few little examples here. This first model is the SIR model with births and deaths. I wrote this before COVID, and so I said, think of the simple model of chickenpox, but really we can think of COVID-19 as an example of an SIR model. The SIR model is an epidemic model used to model diseases on a group of individuals. In this model, we're having S of t represents susceptible, I of t represents those infected with the disease, and R of t represents those who have recovered. And this is the simple model for this, including births and deaths. Now let's make sure that we understand what is going on with this model. We want to know what every single term represents. And so looking at this, we have ds dt. That represents the rate of change of the susceptible population. The first term we have here is a negative beta si over s plus I plus r. What this term is representing is the interaction of the susceptible and the infected. And so what happens when susceptible people and infected people interact with one another with respect to the rate of change of susceptible? Well, when susceptible and infected people interact with one another, that's going to lead to susceptible people getting infected. And so we're going to see a decrease in the number of susceptible people. And those people are then going to be transferred to the infected portion. And so looking down here, we see the exact same term as a positive in the infected. This beta then represents the rate at which people are interacting and getting infected. This can be thought of as how infectious a disease is. We then have this term here, beta s plus I plus r. This is talking about natural birth. And so whether you are susceptible or infected, or if you've recovered from this disease, there's going to be a natural birth rate. The R term we might have to take a look at because R represents removed, and that could include through death. But yes, and so that's how we have this. We then have this mu sub s. Mu is talking about natural death. And so this is the natural death of the susceptible population. And so once they are, if individuals die, then they are removed from the susceptible category. But this is natural death. This is not death related to the disease itself. We then have di dt. Again, we already accounted for this term. This term is saying that the interaction of susceptible and infected is going to lead to an increase in the number of infected. This gamma I term, this is the natural recovery rate. This is saying that people are naturally going to be removed from this population. And the more people are in this population, the more people are going to be removed from this population. The greater the rate of change of the removal is going to be. That's because if you have 10 people who are infected, well, maybe 1/10 of them will be removed. And so that would be one person. Well, if you have 100 people, 1/10 is going to be 10 people. And so the recovery rate is going to be, how people recover is going to be proportional to the number of people who are infected. And that's what this gamma term represents. Mu then again represents just natural death. And then DRDT, well, this is the people who have been removed from the infected category through recovering or dying from the disease. And so that's what this term represents. And then again, mu represents the natural mortality rate. This summarizes a lot of the standard terms that you are going to see. In this birth rate is representing exponential growth. If we wanted to, we could have taken logistic growth into consideration and had a minus b squared term. We could have made this better by adjusting the birth rates for these three values. Are the recovered going to have the same birth rate as those who are susceptible? It could be complicated if we're saying that the R is representing those who have otherwise been removed from the population. In other words, have died and been removed from the population. And so there are things that we can tweak with this model. Oftentimes, the simplest models don't even include the birth and natural death components. And so there are many ways in which we can modify this model. And there's a lot of analysis that you can do on this model too. For instance, if you want, you can consider the ratio of beta to gamma. That'll tell you a lot of information about how infectious and deadly a particular disease is, how quickly it will spread. And so there's a lot of information that you can garner from this model. Our next model is a standard tumor model. And so here is a simple tumor model from the article, A Mathematical Tumor Model with Immune Resistance and Drug Therapy, an Optimal Control Approach. In it, we have four variables. We have I of t, which represents the number of immune cells. We have big T of t, which represents the number of tumor cells. We have N of t, which represents the number of normal cells or host cells. And U of t represents the amount of drug at a tumor site at time t. And so let's take a look at this and see if we can understand exactly what's going on with this system. And so let's go one equation at a time. And so we have I dot. This is the number of immune cells at time t. The first term we have here is S. This does not have any of the other variables associated with it. And what that tells us is that it's not dependent on the number of immune cells, number of tumor cells, or number of normal cells, or anything else. This is just the natural rate at which immune cells are created. If we ignored all of the other terms and we integrated, we would see that this is saying that it's going to be increasing at a constant rate. And so there's always going to be a constant rate at which you are producing immune cells. What that rate is might vary from person to person, and it might actually fluctuate with respect to time. And so this could be an S of t term. But for the purposes of this, it's saying we're going to assume a constant production of immune cells is a natural thing. This term is talking about the interaction of immune cells and tumor cells. But note, so is this term. This term is also talking about the immune cells and tumor cells. This first one, though, is saying that it's positive. And so this term is likely talking about your body producing additional immune cells when immune cells and tumor cells are active or are interacting with one another. And so when there are immune cells interacting with tumor cells, your body is going to begin producing additional immune cells. That said, this term is showing that when immune cells and tumor cells are interacting with one another, it's going to lead to the death of immune cells. And so we are going to see a decrease in the number of immune cells. This term here is saying that if we do not have any tumor cells or normal cells, immune cells will naturally deteriorate. And so we are going to see immune cells go away naturally, no matter what. We will leave this last term for later. The tumor cells, same thing. And so in the tumor equation, we have this term here, R1 T 1 minus B1 of T. This is a logistic growth term. You see a T minus a T squared. This is saying that in the absence of immune cells and normal cells, we're going to have logistic growth for our tumor cells. The second term has the IT. This is saying when immune cells and tumor cells interact with one another, it leads to a decrease in the growth rate of of tumor cells. And so tumor cells and immune cells, tumor cells are going to be dying off. This one is saying the interaction of tumor cells and normal cells is going to have a negative effect on the number of tumor cells. This is likely due to competition for resources. And so when you think of a competition model, if you have a large number of normal cells, which are getting all of the resources from the bloodstream and whatnot, the tumor cells might not have any available for them. And so this is going to have a negative effect on the tumor cells. If there are only tumor cells, then it won't be as important. If there are no normal cells, this term will not have any effect. And again, we'll save this term for the end. The last one is N dot, which is equal to R2. So this is normal cells now. We have this first term, which is corresponding to logistic growth again. And so in the case of logistic growth, we are going to see that it's got a carrying capacity. There's a set amount of normal cells you're supposed to have. Then we have C4TN. Again, this is negative. This is corresponding to the interaction of tumor cells and normal cells. And so when tumor cells and normal cells are interacting with one another, we are going to see that it's going to have a negative effect on the population of normal cells. Again, competition model. And then we have this last term, and now let's talk about it. This term, the F1 of you, F2 of you, and F3 of you, these are all talking about an amount of a drug, because U represents the amount of a drug at a tumor site. And U prime, well, it's going to be given by however it's injected. So this is just saying the injection rate minus the deterioration of the drug naturally. What it represents in each three of these, though, is it's representing how the drug is going to kill off a certain percent of immune cells. A drug is going to kill off a certain number of tumor cells, and the drug is going to kill off a certain number of normal cells. That's how chemotherapy works. You're putting a poison into your system, which is going to kill off all three of these. The key is to then find a stable equilibrium. If you can kill off a certain number of all of these cells, but you can do it in such a way where you have a stable equilibrium, or an equilibrium where the tumor cells disappear completely, then you will have removed all of the tumor cells from the system. And that's the goal. The goal is to remove all of the tumor cells from the system. I think a lot of that's actually written down in this paragraph. How about that? But that's really how chemotherapy and tumors work. We can analyze this simple model quite a bit. For instance, we could say, what happens if there are no tumor cells? What would this system look like? And if there were no tumor cells, and let's say no drug being added to it, then we would just have I dot is equal to S minus D1I. This equation would be gone, and we would just have the logistic growth of the normal cells. And so it would be a very standard system with the tumor cells removed. And so that's a good sign that this model's probably pretty solid. Again, you'd have to find all of the coefficients, and you could do that using experimental data, but you would have to find it for each individual separately, most likely. And so that's how you can start to develop some best practices for how much of a particular drug to inject into a system to remove a tumor. A lot of this work will be done by computers behind the scenes, but at the heart of it is all of this modeling that we have done. This final example that we'll briefly talk about is an Alzheimer's model. And we'll briefly talk about it because I'm not as up to date on this model as the other two. And so here's a model, a more complicated model from 2010 from the article Mathematical Modeling for Pathogenesis of Alzheimer's Disease. We have N sub S and N sub D, which represent the number of surviving and dead neurons. A sub Q and A sub P are the quiescent and proliferating astroglia. M sub 1 and M sub 2 represent the reactive and normal microglia. And A beta represents the amyloid beta peptides. And so the model below shows how the 7 functions relate to one another in an Alzheimer's patient. And one thing that is interesting, and what I found interesting about this, was there was a typo in the article. And it was something that you could notice just by looking at the equations. And that's something that's important because you want to be able to look at the equations and be able to recognize if there might be something wrong there. And so for the A dot P, they wrote DAP dt is equal to negative DAP dt. And so the question is, how can you tell just from the equation that this is a typo? And the way we were able to tell is, in order for the slope to be equal to the negative slope, that's just saying that the slope is always equal to 0. And that's a problem. What they meant was they meant for this A sub P term to be an A sub Q term. And looking through the formulas that they had written, it made much more sense when you've changed it out to be an A sub Q term. And so that's what I wrote up here, is that A sub P, or A dot P, is equal to negative A dot Q. And so that's the end. Yeah. Limits, derivatives, integrals, multidimensional calculus, linear algebra, differential equations. It's all been leading to this fundamental principle. Everything can be modeled using systems of differential equations. That's really the big takeaway from this course. There are other tools that you have at your disposal, such as partial differential equations, and we can model multidimensional things using matrices. If you're talking about a discrete thing, we have the tools for that, which come from matrices or even just individual discrete models. We have a lot of tools which are at our disposal now. For me, I think that the systems of differential equations is the primary one that you should be looking at when you're reading articles. If you can find a differential model, which is taking all of the different populations into account, then you can understand exactly what is going on in a system just by understanding the equations in play. And if you are trying to create a model, well, we now have the tools to do that. Just based on the simple predator-prey competition models, your logistic growth and exponential growth, as well as terms like this S here, which is saying that we have things which are growing linearly, even without any populations, we can have stuff growing. And so with these simple models that we've explored throughout the semester, we can develop and understand just about any type of model. We covered a tremendous amount of material today. We covered real and complex eigenvalues and eigenvectors for systems of linear differential equations and nonlinear differential equations, and a little bit of everything in between. But I think it was pretty good. Y'all have a tremendous amount of homework ahead of you. Good luck with it, and take care of yourselves.